models of huge objects. Inbal.
I cannot wait to not be the chair anymore.
I-
Counting down.
I have a little chart here. I'm enjoying every talk, chairing every talk.
So hello everyone. So I'm going to talk about the indistinguishable generative models of huge objects. And this is a joint work with Omar Reingold and Lunja Hu, which are both here. So I'm going to start by this giving some background and motivation. Then I'm going to say what we mean by having a generative model from a single huge object. I'm going to show how like existing techniques, learning techniques also work in this like huge object setting. Then I'm going to talk about one example where existing techniques don't really work and we need to do more things. And I'm going to finish by presenting some open directions. So for a really start, I'm going to start by like a motivating example. Suppose I want to analyze the graph representing the internet, but I have a really simple analysis I want to do. I don't actually need all of its complexity. I don't actually need everything. I just maybe want to know how much we have connection between two large domains. I don't know, West Coast and East Coast. So I don't really want the graph representing the internet. What I really want is something which looks like the graph representing the internet to my purpose. And I would hope that this thing would be small so that I would not have to store this huge graph. So sort of what I want is a small implementation that for the purpose of my analysis looks like the graph representing the internet. So this is like a high level motivation to keep in mind and sort of.
What's the difference between the model and the implementation?
So the model is, so the implementation is like a random sample out of this model because we want to sort of use the randomness. So the idea is that on average, a random implementation would look like a graph representing the internet. Thank you. So this is like a motivation, and to formalize it, we're going to use a setting by Goldwasser, Goldreich, and Inbal that they talked about huge random objects. But before I'm going to talk about huge random objects, I'm going to talk about the standard pseudorandom setting, in which we're trying to create an object that appears to be random. So for example, we have all n vertex graph, and we want an algorithm that uses less than n squared bit of randomness, but outputs a graph which seems to be random. And what we mean by seem to be random, so like in many previous stuff, we have some class of distinguishers that get either G prime or G, not both of them together. And sort of what we want is that all distinguishers in the class are going to act more or less the same, whether they get a real random graph or they get something generated by our algorithm. So these might be polynomial algorithm, might be less complex. So in the setting of GGM, they introduced the idea of having a random object, which is huge. So in this case, instead of M being like poly n, where n is the runtime of this algorithm here, we can think about the number of vertices as being exponential. And then clearly the distinguisher cannot even read our graph. So in their setting, the distinguisher has query access to either a completely random graph or to a graph, which is an implementation. And then, but the requirement, the indistinguishable requirements is still the same, but now instead of having reading this entire object, we only have query access. So another thing you can see that it's not only that the distinguisher cannot read this entire graph, but also this algorithm cannot write this entire graph because the graph is exponential. So this is why this work is about also implementation of huge random objects, because now, unlike in the normal pseudorandom setting, the algorithm does not actually output the random object. It outputs some small implementation that can answer queries. If this is a graph, is there an edge between U and V? Yes.
Do you assume that, do you allow the implementation to have state and be probabilistic as it's progressing? Or? once you output the key, the graph, there be an actual single graph that's determined.
So like the implementation can be probabilistic, but once you have like for every random string, there should be a graph underlying. Like you cannot answer inconsistent results about like an edge or something.
You both don't have access to the edges and you don't have access to all of the vertices, or is it just the number?
Like, so there is some like graph, but it's not explicitly represented. So it's like represented by this small implementation. So the distinguisher can, so the vertex set is just 1 to n. So the question that are interested us is like, if there exists an edge between certain vertices. And in this work, they also introduced the idea of having truthfulness conditions in which sort of, if we assume our graphs have some additional global property, for example, suppose we look at all n vertex graph that have exactly k edges. This is a global property, so it cannot be verified by the distinguishers, which only can query edges. But if all the graph we're trying to imitate have it, we also want that all the implementation we have should also satisfy it, regardless of this property not being able to be distinguished by our distinguishers. So what we're doing in our work was to take this setting that GGM introduced and to treat this setting in the idea of a generative model. So sort of the high level ideas.
Why is it truthfulness important if you cannot verify it?
So maybe, I have only simple analysis, but over time, I still want to be consistent with the global property I know the graph of the internet has.
So regardless of why, it's not trivial necessarily to achieve. But it's a good question.
I remember you answering it in your talk, but discussing it in your
I can't
talk.
remember why. You know this joke about, well, I'll tell you later. But so let's put it this way. There is a reason one can give, but regardless, it's mathematically, it's a different object, right? That you can support some operations that maybe you couldn't support. Because you could think of a case where you have a trap. Okay, now I remember. Suppose you have a key. So the outside world, it looks the same. But you have something that enables you, because it satisfies some true property, to give answers to some questions you couldn't have understood that. I think the question was some sums of things. But why?
So the random permutation. The random permutations are exactly to the random function.
No, but he can ask, why do you care? You can't tell him
I care about the random permutations because they give you encryption, they give you block ciphers.
For example, so that when you have a trap. So again, I think it's when you can do some operation because you know something extra. That this comes about.
So Inbal user, what kind of access you allow the distinguisher to have?
So I'm going to talk about it, not right now, but like in a couple of slides. So like in a very high level, if we want to create a model which sort of looks like a specific graph, so we assume we have a single huge object and a distinguisher like before. And sort of we want to replace it. So in our case, the distinguishers only receive samples from either the huge object or our implementations, like random edges from the graph. We do not know how to handle queries, and like we have a result saying you cannot handle queries in this setting.
Kind of statistical queries that, like in the graph regularity case.
But not like, is there an edge between you and me? This kind of queries we don't know how to handle. Yeah, so now in a more formal way, we have a single huge object, and we want to have indistinguishable models. So we have a collection of distinguishers, and we want to output a model that outputs now randomly an implementation. And we want this to be the same with respect to our set of distinguishers. So we're actually missing something here, which is that we need to learn this huge object, because this is now a specific huge object. We're not trying to generate a random object. So we have to have an additional step, that has a learning algorithm that has some samples also from our huge object. And then this learning algorithm should generate our model. So this is like in a very high level, and in a more specific setting. Okay, sorry, this I forgot to say. So if the huge object is very complex, then clearly we cannot learn something which is actually close to it. So sort of like in many previous talks here, we're learning it with respect to a set of distinguishers. So we're only learning the properties of this B star with that the distinguishers actually check. And in a more, so we have a set of distinguishers. They have, in this case, this is only sample access and not actually query access, but we still want this to be the same. And in every specific instance, what do we mean? We have a huge object. Now it can be a specific graph or a specific function or other object, but we only handle graphs and functions. And then it is also defined by a set of distinguishers, because the learning algorithm now has to know ahead the set of distinguishers you need to be indistinguishable with respect to, because else it would not know which properties of this B star it needs to learn. And if we have truthfulness conditions, then we also need to know them ahead of time. So all of these like define the instance, and this is the setting we learn. And our result. So what we're going, so we introduced this idea of having indistinguishable generative models for huge objects. And in some cases, existing results, like I'm going to talk in a moment about the weak regularity lemma, just works directly also in this setting. In some specific cases, standard results do not directly work. For example, if we want a truthfulness condition. So in the work of GGM, they had a random function with a fixed support of size k. And we can also do it in the case that we're trying to learn a specific function with respect to some set of distinguishers. It is more complex because sort of you need to trace exactly how many ones you gave to any kind of subset of your set, but at the same time to be similar to your input function. And also we show a result about sparse graph that I'm going to talk about later on.
So, very nice. So let me just summarize in my own head. So you're saying today in learning, they come up with generated models, and their definition of what success is that you cannot distinguish outcomes from different real. Yeah. You're saying in addition to that, you want to impose on these things that you cannot distinguish something that's true.
Yeah.
Very nice. Now, in the same way that somebody here asked why, I ask you why. In your context.
Yeah. So in our context, what I can think of is that sometimes maybe, you know, I only want to run a very simple analysis on my internet graph.
Okay.
Yeah. But like over time, if I know the graph has some large property, I would like to keep it because it might affect things. But I don't have like a very specific use case to why we might want to put that for the specific function case.
If I throw away the truthfulness requirement, is that basically a special case of simulating a function? Because you can just build the domain is v times v, and then the function is the true edge function. And I'm just trying to simulate it in a way that you cannot distinguish a random sample from the true function and the random sample from the simulated function.
I'm not sure I understood the question.
If the distinguisher only have sample access, and the sample access means give me U and the V from the possible, and tell me whether there is an edge or not, and then U and the V is from some distribution. Isn't it just the same as learning a function where my domain is basically now switched to v times v. My function is basically the edge function, and I want to find.
So for a graph, you can treat it as like you can reduce from learning a function to learning a graph. If that was your question.
I feel you can also reduce learning the graph to learning a function. Basically, the function has a special domain.
So the specific,
Same. It's
Yeah.
the same
Yeah.
object.
Yeah, so without the truthfulness, it's not.
so in the specific case of sparse graphs that I'm going to talk about, there is also something that at least we don't have a function analog for what we can do for a sparse graph. So I think I would just get that later on. But the standard result about just learning a function with no restriction and learning a graph with no restriction are practically the same.
Yeah.
Yes. Okay, so I'm going to start by like existing result, how they just work, which is, I think, we saw quite a lot, but I'm going to define, so we have an object, it's a specific dense graph. It has all of n squared edges. We have distinguishers, they only receive a single edge. So this would be a single random edge. Each one has two sets of vertices, and it accepts if U is in V1 and V is in V2. So this is the standard setting of the weak regularity lemma that was actually mentioned here quite a lot before. And in the simplest case, where we have disjoint V's, you can even think about just having 4 sets of vertices, and distinguisher just check how many edges are between these 4 sets. Then our learning algorithm just needs to know in this graph G prime, what is to approximate what is the edge probability with respect between each of these sets. And then the model could just be these 4 sets and the probabilities between them. Now, because we're in this huge object case, we also need to have an implementation. So in this case, we can easily do it by rejection sampling. We sample because we need to generate samples from our implementation. So we sample 2 vertices, and we just output UV with probability PUV, and with probability 1 minus PUV, where PUV is just the P of their groups. We repeat this. And this would work as long as this P is constant. So that would stop. It's not going to work for a sparse graph.
Yeah. So are you trying to answer queries? You're trying to generate samples?
Generate samples from a graph that looks like this G-star.
And PUV is the fraction of edges in the graph that are between U and V, or?
Sorry, PUV is just the probability, which is like they say P12 if U is in V1 and V is in V2. So this is just so my model just remembers like the fraction of edges between the 4 vertices.
The fraction of edges in the graph, or the fraction of edges out of all the possible edges between V1 and V2, how many edges actually exist?
Yeah, like it approximates like the probability of a random edge between V1 and V2 in G star.
And when you say sample U and V here, you mean
This
sample
completely
cluster, or?
no, these are completely two random vertices.
And PUV is like the PUV of the cluster.
Yeah, of
U
the
is in,
cluster
and
they
the
belong,
cluster that V
yes.
is in.
But if we have a slightly more complex set of distinguishers, which are learnable, so what I mean by this is the same as I think was in before here, that if we have some D distinguisher that has 0 more than epsilon, then we can approximate these sets U and V that are the set of this distinguisher. And then by a boosting algorithm, which is actually the same mixed membership model as GTV, we get a mixed membership model like the same result exactly. The boosting algorithm gives us a mixed membership model. And now PUV is not just P of the part that belongs to U and V, but like a sum over all partition of the boosting algorithm. So this is like the existing work, just we have this extra implementation, but this would not work for a sparse graph.
Inbal, I think sorry, I think I missed the setup. Can you go to the last slide?
The one before?
The one before, yeah.
You have to output an edge, not a pair of vertices, and say if they are connected.
Yeah, you have to output like a random edge from your graph.
So the object is just an arbitrary graph that
Yeah, it's like a fixed arbitrary graph that you're trying to imitate.
and then how you are learning is by learning a partition.
So the partition here is given by the distinguishers. So I assume the distinguishers have partition that we know about it.
Oh, I see, I see. And then the distinguisher is just checking whether the density
Yeah, they're just checking that.
is observed.
So this is exactly the setting of the weak regularity lemma. If we generalize this set of distinguishers to be, if this is just a set of distinguishers is like a learnable set of distinguishers, then the boosting algorithm of TTV for when viewed in the weak regularity lemma is going to give this model. So
Slightly different from what I remember. Isn't that in the graph regularity that the distinguishers are cut and then what you want to learn is a partition. But here you say the distinguishers is a partition and then.
So this, I mean, the distinguisher checking whether there exists an edge between two sets of vertices is actually a cut.
Yeah.
So this is why it's sort of the same. So in this case, would it work for a sparse graph? So in a sparse graph, the total number of edges is both n squared n. So first of all, the error in the case of a sparse graph, if my distinguisher receives a random edge, the error scales with the number of edges in the graph. So this means our error is something like not epsilon n squared, but epsilon n. So this can be a problem because the normal boosting algorithm would just give us an n squared error. But also we cannot do rejection sampling because we are in this setting where we have huge object and we want to generate edges from it. Sort of, we don't know how to generate random edges from a sparse graph based on these models. So what we do is sort of cheat because we create a dense model for the sparse graph that we get. So the idea is that we have, even if we know the graph is sparse, we still create a dense model. We know it's not going to be close to our graph, but sort of with respect to the probability of a random edge to cut, to go through all the cuts defined by a set of distinguishers, we're going to be indistinguishable. So this is our theorem. If we have a sparse graph, but we can only do it for a sparse graph that have no dense subgraphs, and we have a learnable set of distinguishers, then we can output a model that is indistinguishable with respect to a set of distinguishers. And the way we're doing it in a very high level is by using the strong regularity lemma. Yes.
Can we go back? So what does it mean that T is learnable?
The same set of distinguishers I had before, that each distinguisher receives like an edge and accepts if P is in V, and if there is a distinguisher that is not that has a large.
So there's like an information theoretic result here, but also a computational result. You're saying first, whether they're learnable or not, you can build an object.
Yeah.
If they are learnable in polynomial time, then maybe you can even learn it in polynomial time.
So if we do not have any kind of learnable restrictions, this is in some sense that like just derived from the regularity lemma, the strong regularity lemma. So like the interesting case that what we have is that we still need to learn it. Okay, so in a very high level, what we're doing is we receive our learning algorithm receives samples from our sparse graph G star, but from the strong regularity lemma for sparse graphs that have no dense subgraph, we know that there exists a dense graph G prime that is indistinguishable from our input, and this is indistinguishable in not with respect to a set of distinguishers, but actually in this like for any cut, like in the strong regularity lemma. So this is for the strong regularity lemma for sparse graphs. And we sort of pretend that our algorithm have sample access to G prime and not to G. And we're learning this we're learning this model for G prime, and then we show that this model is also indistinguishable for our original graph G. And at the previous, we don't have an analog of anything we're doing here in the case of a function, because sort of the idea of a dense graph without, a sparse graph without dense subgraphs, this entire object does not really have, or at least we don't have an analog for that in the setting of a function.
Well, there are generalizations. I mean, this is essentially the graph version is a special case of the dense model theorem.
So you're saying we could be using the dense model theorem, we could find a function analog for this?
Yes.
So that's interesting, and I would look into it.
Okay.
So in a high level, this is what we're doing in the case of the sparse graph. And I'm going to finish by talking about open question, because we sort of view this work as like introducing this model, and there are a lot of things that we don't know how to do. And I'm going to talk about some of them. So the first thing is we only handle functions and like binary functions actually, and simple graphs. We have some results about non-binary functions, but they're not very interesting because we don't know how to do an interesting set of distinguishers. So I think this is very interesting to try and figure out if we can do something there. And for this, that's actually about your comment. Currently, the only result we have for a sparse object is this sparse graph. And that would be very interesting to see if we can extend it to some sort of sparse functions or find other sparse objects, because it seems to be inherently more difficult to handle sparse objects than dense ones. Also, currently, the distinguishers we know how to handle are sort of independent, like a single edge or a single entry, but we don't know how to handle distinguishers that like take multiple edges and try to check if there exists some subgraph or some sort. And that would be very interesting to handle. And also, if we can do truthfulness with respect to more properties than like the number of edges, total number of edges, or the total number of ones in a function. So this is it. Thank you.
Have time for a question?
Oh,
Go ahead.
go first.
Go ahead.
Okay, so in your notion of implementation for this kind of generation, you have like a sampling procedure that gives you random edges. But as far as I can tell, directly, you don't necessarily get a particular graph that you're sampling from. That you could, in principle, be sampled from any particular edge if you like sample enough.
Right. Yeah. So.
But you could like do something. I think you could do something a little bit different and have a particular graph in mind. Like take a pseudorandom function and use that to define whether you're doing the recursive sampling.
Yes, that's actually, I was sort of ignoring it in the talk, but actually in the work of DGM, they showed how you can do it with a pseudorandom function, and we're building upon the result. But yeah, for simplicity, I didn't mention it.
Okay.
Yeah, I wanted to ask, like, I remember there are algorithms that uses this sort of graph regularity to show that for dense graphs that the whole set of and the reason that they only stop is because they only can simulate dense graph. Otherwise, the error, which is epsilon with a fraction of v squared, it will be too large. But now that you have something that simulates a sparse object, I just wonder if there's any.
The
learning
problem might be hard.
Where would it fail?
So, I mean, it might be first that sparse graph with no dense subgraphs are still easy with respect to, because this is not on any sparse graph. We sort of need, And we also know that if we have a sparse graph that have a dense subgraph, at least our method doesn't generalize.
Okay.
So it might be that sparse graph, because these sparse graphs are sort of random-like. They're sort of uniform, so it might be easier on them as well.
I see. Thank you.
Can I ask questions? Sorry. So since you have transported this idea of truthfulness to, I mean, to a large, to a generator setting, I was wondering whether some kind of incremental definition would make sense. So if their thing exists, now you right, you have to say properties on it. There's no notion of building it up. You're building it up. So the reason I was thinking it is because when somebody asked you, but why would you want it? You're saying, but maybe in the future. This kind of remote power. Thinking about the idea that you have an object and now you want to extend it in the future.
Like to refine with
Or
a
to make
larger
bigger-
set of
I mean,
distinguishers.
say you have a graph, you have an internet. The internet is going to grow.
Ah.
The internet is going to grow, but you want to make sure it doesn't grow. Something is true about this growth.
Grows with it.
So you think it would be interesting to think about how you have an object and you want to get a bigger object. So
Like over time.
over time and how much it would cost you to make it bigger and still maintain the global population. It's just something that will not come up. In the,
Yeah, in the random one. So there are-
no, because you have an object and now.
Yeah.
So we have a lunch break and we should all be back here promptly at 2 p.m. Next session. We get on time.
For Guy Rothblum stuff.